scroll through the Wikipedia page because it pretty much has everything you might ever need or want on configs.
Fair enough. That's a presentation to me. So
good. Okay.
Before we get started, did anyone have any questions or comments from their deliberations while we were gone, or while we were
stuff from
away?
last time?
Yeah.
Possibly.
No worries. Just wanted to throw it out there.
Okay. Welcome to the wonderful Wikipedia page about how to stick your wing on your plane. So you could have the perfect performance target from all of Laird's stuff, but you could absolutely screw it up if you pick a wing layout and general configuration for your aircraft that is not conducive to your goals, and everything will be way harder. So like if you built one of these, but you were trying to make like a super maneuverable light plane, you would have a bad time because this is not designed for that at all. So that is why it is good to know the benefits and like best implementations of a lot of different layouts. So this pretty much just talks about wings specifically, but I'm also going to talk about tails near the end since it's a pretty similar concept, although tail design by itself is like a whole other thing. And I'm also going to cover fuselage layouts because they're pretty much covered in here a little anyway, but they're just as relevant, and you kind of figure out your fuselage and wing layout at the same time for the most part. So yeah, I don't think anyone would have questions yet, but if you do, just call them out because I don't think I can see well, I figured out how to bring up the thing where you could like raise your hand, but I'm probably not going to notice. So just start yelling at me. The primary considerations are basically the shape that your wing or wings have in like all three dimensions. So the like cross-sectional shape and the planform shape in the like okay, well, we should define some axes, which I don't know if any of you guys have seen this. If you've been in 121, I think they at least cover this a little bit, but it'll help us talk about stuff. So the lateral axis is the one that passes through the wingtips. The longitudinal axis, aka the long direction, goes from the nose through the tail, and the vertical axis is vertical. So try to keep this straight. I don't know. I don't have any like tricks for that, but we're gonna reference that. So in the lateral direction, you're mostly like that would vary your wingspan, and in the longitudinal direction, that would vary your chord. And you're gonna know generally what like what wing area you want and maybe an aspect ratio after you figure out your performance, but it's still up to you to lay out that area in the best configuration. So that's why you need to figure out the shape, and then the position is going to affect your performance more like granularly, and it'll affect your controllability as well. So the where you put your wing will determine a lot of how your plane flies, and it'll also eventually impact how you design your tail, because the wing and the tail, I mean, as a quick aside, the entire point of having a tail on your plane is that if you only had a wing and a fuselage, it would like continuously nose up forever, like no matter how fast you're going or whatever, unless, as we'll see it farther down, you could specifically design your wing in such a way that it acts as a tail also, but like a normal plane, air quotes, doesn't do that. So balancing the wing and the tail becomes its own whole thing. But you can control a large portion of how the plane's going to fly in the first place just by where you put the wing. So yeah, shape of the wing and position of the wing are the two major variables in choosing a configuration. And that's why it talks about those a lot. Airfoil selection, yeah.
We'll have a class
Yeah.
covering basically that, a whole class covering why we need a tail on one of the axes. The analysis is just on one axis for most of it.
The tail is
Your
really
third year.
important for control for in the pitch axis, which back to here, pitch is like rotating around the lateral axis, so moving the nose up or down. Roll is rotating around the longitudinal axis, so like putting one wing up or down. And yaw is rotation about the vertical axis, so like moving the nose left or right. And in case anyone didn't already know this, the way a plane turns, like changes which direction it's flying over the ground, is not by yawing, even though you would think like, well, you just turn sideways. It doesn't really work that well. So instead you roll so that and also the angles between, like the angles that we use to define which way you're facing are your pitch, which is in the pitching rotation, your bank, which is like if you're rolling, you're changing your bank angle, and your slip angle, or I think beta, for rotating about the vertical axis. But so if you want to turn the plane, you change your bank, so you roll over to the side and then hold your pitch steady at 0, and the lift that's pointing sideways is what actually makes you turn. So when you're not banked, your lift is just perfectly balancing your weight, and you don't change direction. But if you're banked, then some of your lift is going sideways. That's why it says horizontal component. And that like pulls your aircraft to the side. And also because of the tail, like instead of just drifting sideways and pointing forward, it like changes so that you're pointing in the direction that you're sliding, basically. And so if I could back myself back up to what we were talking about somehow.
You're talking about airfoil? You started saying airfoil something?
So you need, like, we're going to talk mostly, like I'll talk about this a little, but you also have classes on this and stuff here in airside. The elevator, which is it's the one that looks like a tiny wing on the back that controls your pitch, is the most important for controllability, like from a high level, because it's the hardest to design well, and your ailerons and rudder are still important, but you can kind of like, there's a lot more leeway in how you design them. Whereas if you design we call this the horizontal stabilizer, the thing that the elevator is attached to, but sometimes you just call the whole thing that, the size of that will directly affect like if your plane flies correctly and how easy it is to control. So that becomes really important.
Is that why birds don't have a rudder, but it's because it's not technically needed?
Yeah, because they have such good like internal mental control algorithms that they use their tail as a rudder basically by just turning their whole body like side to side, and pointing their tail like to one side or the other. And because they're not like perfectly flat like this thing, the whole point of an elevator is basically that it has no like impact on the flow in the other direction. So if you have a plane elevator, it should only direct air up or down, not left or right at all. But birds are like, nah, fuck that. We'll just do both at the same time. And there are some planes that have,
yeah, like a drone, right? Like a predator drone.
Yeah,
tail.
That's another example. So there are some planes that have kind of mimicked that intentionally, but we'll get into that a little later with the tail stuff. So yeah, and then as far as choosing like the cross-sectional shape, that's called the airfoil, because I don't remember why. It's probably French or something, but it's well, Airfoil Tools, which is a website that we'll use later. But it's like this kind of shape, the one that looks like that, and they heavily influence like how your wing will fly, but you don't need to like choose that to choose a configuration, because a wing with any like planform shape can still have whatever airfoil you want. So you can define like this part of the shape completely separately from this part of the shape. And this is like more performance calculating stuff, because once you know like what performance you want, then you can try to find an airfoil that will achieve that performance. Yeah, so we'll talk about that at a later date. So for now, the main parts of the shape that we're focusing on are the planform shape, which that word means like what it looks like from the top down, basically. So this planform shape would be like two rectangles like that. Yeah, here, we're gonna get into that. So, okay, I think I can start talking about actual configurations now. And I'll just go in this order because why not? The placement of the wing, like relative to the fuselage, up or down, will determine, if you think about it like balancing. So the center of mass is, hopefully you guys know from like physics and stuff, the point where if you were to take all the mass of the object and like concentrate it at a single point, that would be the same point as it is for the whole object, aka like the balance point. And so the fuselage is probably more of the weight than the wing in most planes, like and the wing will kind of do its own thing no matter what. So you can think about where you put the fuselage as like how you want it to be supported by the wing. So if you sit the fuselage on top of the wing, aka a low wing, you're kind of balancing that mass from the fuselage on top of the wing, which isn't that big a problem, but it means that like a lot of planes like this will have dihedral, which we'll see later, because it helps like create natural stability instead of if you're balancing it like that and you have like negative stability, for example, it would have a tendency to like roll by itself more easily, compared to if you put the wing above the fuselage, which this like what it's calling a shoulder wing and a high wing, these are basically the same thing as far as we're concerned, because when we make high wings, we just put them against the top of the fuselage. But you can kind of think of this as hanging the fuselage under the wing, so it will tend to have a little bit more inherent stability because it's like a pendulum or something, as opposed to like the opposite of a pendulum, whatever that is. So and the effects are relatively small because again, it's not like the fuselage is like way up here and the wings way down here, and hopefully you can see my mouse and see what I'm talking about. But the other main thing this affects is in a manned plane would be visibility, but for us it's like ground clearance, and it has like some minor performance impacts basically, because a high wing can, like the fuselage can kind of mess with the flow on a high wing more, since a lot of the important flow stuff happens behind the wing than in a low wing, but it's not that different. So vertical placement of the wing mostly comes down to like other stuff. It's not that often a performance consideration. Okay, how many wings? There's a lot of like biplane data and stuff, but it's all from like the 30s or earlier because we kind of stopped making biplanes after that. But really the main benefit of a biplane is you have twice as much wing area because you have twice as many wings. Not exactly twice as much if your wings are different sizes, but unfortunately you don't get exactly double the like lift from a biplane as if you had one of the same wing. But you do get an improvement. It just has diminishing returns. So like this plane with like, what is that? 6 wings or 7 wings or something. It doesn't have 7 times the lift as like if you had just this plane with one of those wings, because there's just a lot of air and stuff going on that will keep it from scaling infinitely like that. And the other big challenge is that you don't want the wings to move in relation to each other. So that's why they all have this like bracing wires and stuff. And basically this ends up, the reason this isn't very popular now is it ends up having a much bigger drag penalty than is worth it for the additional lift. So all biplanes are basically really slow. These wires that they're using to brace it were fine when your like top speed in any plane was like 40 miles an hour. But as you will learn eventually, a cylinder, which is what like a wire is just a really long thin cylinder. A cylinder is like the draggiest possible shape. So we try to avoid those when possible. So yeah, you could consider a biplane, but for this goes for kind of everything, but any design decision you make, you have to justify. And the easiest decision to justify when there's no other factors that influence it is like whatever the most common or default thing is, if only because like there's the most data to go off of and like it's the easiest to implement usually. So anything we talk about is up for consideration, but the weirder or like less common it is, the more you have to, or like the more solid your justification for using it has to be in like a competitive environment. For mock comp, I would say that still applies, but we give you guys a little more leeway because like it's also fun to just make weird stuff sometimes, but we're not, you're probably not going to do so hot if you're like, yeah, we built a plane with 4 wings because we wanted to. So that's why we don't have any biplanes at DBF currently. You could stagger the wings and you would get slightly different like control characteristics, but we don't do biplanes that much, so we don't really need to get into that. I think it's only mentioning cruciform wings. Oh, yeah, I guess it might not talk about tandem wings very much. I thought it did later, but oh yeah, it does. Okay, so I think it's just mentioning this because it feels obligated, but basically this is a helicopter and this is a missile, so not really our deal. Okay, methods of supporting the wing. This is a little bit into the structure zone. But basically this is just saying you could either have it be externally braced or internally braced, and internally braced is also called cantilevered because like in what class, like structures, CE something, a cantilever beam is one that's just like attached to the wall and it supports itself. So that's this style. Struts are, the difference between like strut braced and wire braced is that wires only exert force and tension. They don't, they like if you try to compress them, they just collapse. Whereas struts can hold tension or compression forces. They usually still are in tension because they're prone to buckling relatively easily still in compression, but they're more compressible than wires. Yeah, but that's still usually about biplanes. There's still a good number of like small aircraft, like general aviation aircraft these days that are strut braced, but the large majority of planes are cantilevers now. So although we technically still do wire bracing sometimes, like for our tail, because at the scales we build at, our tails tend to get very thin. And if you have like a single balsa stick thickness tail, it's not going to have very much stiffness like in the lateral direction. And so adding a couple like strings basically, since wires would be unnecessarily heavy, is sometimes a method we use to stabilize it. But the other option is just make it a cantilever by like thickening it and using a different profile. So closed wings, I feel like what are we on? I guess this is considered wing support, but this also has more performance implications than this stuff. So when a wing is generating lift, it is one of the major contributors to lift is the pressure differential from the bottom of the surface of the wing to the top. And we don't need to get into that much right now, but we can talk about it later if you want. But basically that means that at the tip of the wing, the low pressure on the bottom wants to spill over into the high pressure. The high pressure on the bottom wants to spill into the low pressure on the top. And so it tries to like curl around the wing. But instead of just doing that and sitting there, the wing's moving forward through the air. And so it like curls over, but then it basically spirals behind the wing as the wing's moving through the air. So that's why you get these vortices. And I think this, yeah, there we go. This is like the most iconic picture ever that I love very much of a vortex, but the pressure is curling around to the top of the wing, and it's really visible here because of whatever they're spraying, but it just stays like that and spins. And it looks cool, but it's terrible for performance because all of the energy that's going, like that your plane has, that's going into creating this vortex is not going into lifting the plane up. So you're losing, like the stronger this vortex is, the more lift you're losing basically. So the smaller you can make this vortex, the more lift you can keep for lifting the plane. So it's going to talk about winglets later, but one way of dealing with that basically is not having a tip to your wing. So if the wing just like goes all the way around, then the low pressure on the, or the high pressure on the bottom has a much harder time reaching the low pressure on the top. So even though it like wants to, air quotes, it won't form as strong of a vortex. And so your like efficiency of your wing will be higher. So these are different ways of closing off the wing, which it's under support because that means you can have the wing kind of self-support more if there's like two of them. But it also will help with your performance. Flexible wings are basically kites, so we don't have to worry about that. Okay, on to actual plan form. So there's a bunch of things that you can change in the plan form of your wing. And I guess we'll just smash through them. The aspect ratio, which I think you guys talked about at least a little with Laird, to recap, is the ratio between the span or like lateral length of the wing and the chord or longitudinal length. So that means the wider the wingspan is relative to the chord, the higher the aspect ratio. So like a glider they tend to have very high aspect ratios. So really long, skinny wing. And then like a fighter, like an F-104, they tend to have much lower aspect ratio wings, so like really short, stubby. And that the greater your aspect ratio, generally the lower your induced drag will be. And induced drag is created anytime you're creating lift, and it's kind of related to the vortices I was talking about. But basically, like the more you spread the lift out away from itself, the less drag you're required to have from creating lift. So that's why a higher aspect ratio is like desirable on most designs. Fighters are really the only ones that frequently have low aspect ratios, and it's because they're like the lower your aspect ratio, basically the more maneuverable your plane is, for a couple reasons, one of which is like just moment of inertia. Like the more you spread the mass out in the wing, the harder it is to move around. But high aspect ratio wing is also harder to like construct well, because you need more structure farther away from the fuselage. So the whole wing can tend to get heavier because like the thickness that you need to have enough like stuff in there to hold the end of the wing up is greater than it is in a low aspect ratio one. And something about speed. Yeah, I don't know. Hopefully it's kind of intuitive that like short stubby equals faster than long skinny. But yeah, that I think covers that. Yeah, it's going to talk about variable geometry later. Okay, so the chord can be varied like as you move along the wing, and there's some different reasons you would do that, but you can basically there's a whole bunch of ways you could taper it, which if the wing has taper, that's usually implies that the like points connecting the root. Oh yeah, so also if you didn't know, we call the part right next to the fuselage the root, and the part right or like as far away from the fuselage as it goes the tip. So you can vary the chord or the like longitudinal dimension of the wing from root to tip, like over that distance, and different ways of doing that are what this is talking about. But taper is basically means that the root and the tip are connected by a straight line usually, whereas if you just have like a functionally defined thing like by an ellipse or whatever, then you still have a taper ratio, which is the difference between like the chords over time, or you could have a taper function, but generally we wouldn't say that this wing has taper. We would say that it uses an elliptical function for its planform. So the reason that it's good to taper the wing normally, like trapezoidally, don't think I've ever seen a plane that looks like this, so I wouldn't recommend starting off with that. But this is good because if you have a rectangular wing, then when the plane is going to stall, it'll stall like at the tip of the wing first, and that's where your ailerons are, which means as you're stalling, your ailerons stop working, which is bad basically. And so it would be better if the root of the wing stalled before the tip, and you can force that to happen by just making the root of the wing thicker than the tip. And if you taper it correctly, then you can either make the whole wing stall basically at the same time, or you can do it a little more and make the inside stall first, which means your ailerons are more effective for longer. And it, as far as I remember, doesn't really have a major performance impact because you just keep the same area. So it's not like you're just cutting off sections of your wing area. You just expand this, like the root chord, more than what the rectangular, I don't know where we just went. Your root chord becomes greater than it was in the rectangular one, and your tip chord becomes smaller than it was in the rectangular one. So
Isn't
your
it-
okay, it's the same.
Doesn't it limit the effect of the vortices because you're coming off of the tip because you're making that the amount of lift generated at the tip smaller, so the effect of the vortices will be smaller?
I don't know that for sure, because I think the vortex strength is more dependent on the like total pressure on the bottom, because it'll basically want to slide out no matter what. But it might have an impact. I just haven't seen taper used as like a vortex limiting strategy. But I mean,
Okay.
you're the one that's in 405, so you tell me.
And there's also structural benefits too, is there
Yeah.
not?
Yeah. So I mean, if you have structure specific questions, talk to Becca, because she's done a lot of work on this and I've done very little. But for the same reason that low aspect ratio makes the structure easier, the way that airfoils are defined tends to take into account the like you have to define the thickness of the wing somehow. So like in the vertical direction, that dimension. And it's usually like all the factors in an airfoil, the reason you can just apply them to any wing is that they're dependent on the chord, basically. So for a wing of any, or like a wing slice of any chord, because again, an airfoil is just a cross section, that chord dimension will define all the rest of the parameters. The airfoil just contains like the function that turns the chord into each of those parameters. And so the thickness, basically that means the thickness will vary with the chord. So if you have a bigger chord, the wing will be thicker here than it will be at the tip, which means you can stuff more structure into the wing here where you need it, because here the wing is supporting like all of this, whereas here that part of the structure is only supporting this stuff. So this can make designing the structure easier than if you have a constant chord where you could just like change the airfoil over the length, but that's harder to accomplish usually. And so you generally will have a constant thickness in a wing like this, and that means that your structure here, if you just have the same structure running all the way down, which you don't have to, there's other ways to vary it, but like in general, you would have an overbuilt structure. I mean, you would have to build the structure here strong enough to hold the whole thing. And if it's the same all the way down, then that means the structure here is way stronger than it needs to be, which means you have excess weight. Okay, you can also change the taper over time if you want, because you can get basically the same effect of like it'll stall here instead of here, which is better than stalling here first. So, and that can let you like stuff in more area, because like if you had this, but you were like, okay, but what if I just want more free area? Then you could just have the first part be rectangular. Okay. Now, the reason you might use an elliptical shape instead of a rectangular one is, you know how Laird was talking about the lift distribution? So that is, oh, I don't know why I forgot to mention that in the first place, but the taper, like having taper will also improve your lift distribution. So, or at least this kind, I feel like this kind of make it worse, but a constant chord wing doesn't have a great lift distribution, because the ideal lift distribution has been like experimentally shown to be this, which is called an elliptical wing, because the ideal lift distribution is like a half ellipse, and the wing planform that creates that lift distribution is not an ellipse itself, although if you use an ellipse as your wing planform, you'll get really close still to an elliptical lift distribution. So sometimes that's used to approximate it. But this is basically the wing shape that the Spitfire had, because they figured it out in the 40s and they were like, oh, we should just use that. It'll be so good. But it turns out it's like hard to manufacture and stuff. But it means they did have a plane for a while that flew an elliptical planform. So that was cool. And yeah, so like if you choose this design, you would want to have a really good reason that you need a perfect lift distribution, because it's harder to manufacture than the other ones. Again, because although this shape would be like easy to cut out on paper, if you think about the airfoil, that means the airfoil is changing like literally according to this function that you would then have to reparameterize into like 2D and then somehow manufacture like that. So it's harder than even this is like, okay, that's at least just a bunch of linearly varying airfoil sections. Okay. These are a bunch of really weird wing shapes. Circular planes are actually, they fly pretty okay. They are very, they fly at really high angles of attack usually, but they're like flyable at least, whereas the rest, and they're kind of easy to build, but the rest of these are just kind of weird. Okay, deltas are very popular because they basically have built-in sweep, which we're going to talk about next. But they, yeah, so they're good for going fast. They have a good balance of low speed lift and high speed, like lack of drag. But a lot of their benefits don't apply at the speeds we fly at. So it's usually not really necessary for us to use a delta wing, and on the contrary, we're usually giving up performance if we go with a delta, because you have to fly pretty fast to get the like drag reduction benefits, and so they have like pretty high induced drag at slow speed. For example, the MiG-21 that's mentioned in here, this thing has an insanely high stall speed, which means it's hard to land and stuff. So the how you implement the delta also can get into the tail, because a lot of delta planes just don't have a separate like horizontal tail. They'll just slap the control surfaces right on the back of the delta wing, and then those are called elevons because it means they're acting as an elevator and aileron combined. And so you just combine basically the like deflection inputs. So if you want to both like pitch up, then the elevator would move up. But if you also want to roll left at the same time, let's see, you would do that. Then like you would just have one, like you could start with both of them, both L1s pitched up, but then the right one, yeah, would just go back to neutral. So like, or like not be deflected the same amount, so that you're getting a pitch up like elevator input, but not equal on both sides, so that you roll at the same time. So yeah, there's several combination control surfaces like that. Okay, sweep is cool, but sadly it's usually not that like relevant to us, because the main benefit of sweeping a wing is that when you start to approach Mach 1, the drag gets really high, and you can kind of get around that by just having less, it's called apparent flow, I think, or something like that. But basically the chord of this wing is perpendicular to the wing, no matter which way the wing is facing relative to the airflow. So like if the chord is this way, then what that really means is that like the air, or the wing sees the air as like only the component that's flowing parallel to the chord. So in this, I don't know if I can draw on this quickly and easily, but basically if the air is coming this way, then like this, the part flowing across the wing this way would contribute to lift, and the part flowing across, which therefore would contribute to drag, and the part flowing across like perpendicular to the chord basically doesn't have an effect on performance. So you can like kind of reduce the drag at those higher speeds for free, basically. Like you don't get the lift out of it, but you just can shed some drag. And so that's why most, or yeah, all planes that currently fly that get either close to sonic speed or that are supersonic will have swept wings, because it'll reduce their drag penalties in those flight regimes. And again, the air, none of the air is actually moving like sideways or this way. It's just that the if you look at it from like the perspective of an airfoil section, like in the chord direction, then it's seeing the air as coming from like an angle. And so then you can just treat the components of the movement of the air as like in the direction of the chord and perpendicular to that direction. But so our planes don't exceed like 0.15 Mach or whatever. So we very rarely have to worry about that. For like structural reasons, sometimes it can still help to have a tiny bit of sweep. So like if you build but usually it's not that you're trying to add sweep, it's just that you want to add taper. But like see how this tail, it's mostly about tails basically, but this tail has taper, but it's not like since the back edge is flat, this wing has taper and is technically like unswept. It's a straight wing. This tail is technically swept because the line that connects like the center of its tip and its root is not perpendicular to the longitudinal axis. It has an angle, and that's technically the sweep angle. But really we do this because like it requires more structure to make it stable if it's not swept on the, like especially on the tail. Because if you think about like if this point, like if you did the opposite and made it swept forward, which is a you can do forward sweep, which has been experimented with, and it's harder to build and stuff, so it's not very common. But if you imagine sweeping this forward, then any force acting on that front tip of the tail would be like amplified, because it's like if you stick your hand out the car window and like point it forward into the flow, then if the air like kind of catches your hand or like starts to deflect it, then it will start to deflect it more and more, like the force increases. Whereas if you trail your hand like out the back of the window, then the air kind of supports your hand. So like if you deflect it, it pushes it back towards neutral. And so the same thing applies here. So if the like center of pressure on this surface is in front of basically the middle of its attachment, then the air can like catch the surface and it'll push it farther and farther away from neutral. Whereas if you design it like this and put the center of pressure behind the attachment point, then the air will like kind of be a restoring force. So the structure is a lot easier to build. And I know this very intuitively because I built a tail that was completely rectangular and it fluttered off of the plane like 5 feet after takeoff, like 5 feet off the ground. And then the plane exploded after it crashed. So it wasn't good. Yeah, so that's basically the only time we really use sweep though. Like it's saying this is a straight tail because it's saying this is a swept tail. And yes, the sweep like Mach effects also apply to the tail. So like this is more useful, but technically anything that isn't directly like that, the what's it called, the span line, I guess, isn't perfectly perpendicular to the longitudinal axis is swept. So remember that. But yeah, if you're cool like an F-14 or whatever, you can change your sweep in flight. But again, we don't need to do that. And if you're weird, and I think Burt Rutan built this plane or whatever, NASA definitely flew a test plane like that. But the swing wing has like the same theoretical Mach benefits of a normal tapered wing, but it just makes some really weird controllability problems. So it didn't really go beyond initial development. Varying your sweep would help at supersonic speeds for various things, but we can pretty much just skip over that. And then asymmetrical is definitely doable. There's actually a few planes that have asymmetrical layouts, but they're just a lot hard. Like they require a lot more math and stuff. The idea behind this, which is at first actually seems like kind of a really good idea, because on at least a propeller-driven aircraft, because all propeller-driven aircraft have a motor that spins to drive that propeller, and the combination of the motor and propeller spinning basically is a torque on the rest of the plane that if the plane wasn't a plane and it was just a tube, the tube would spin exactly opposite to whatever the motor spun, and you wouldn't actually like get very much power out of the motor. And so all the surfaces contribute to a torque against the engine that like keeps you level. So whenever the motor is spinning, the tail and wing are like creating a counter direction torque moments. Yeah, we'll just call it a torque. And it would seem like, oh yeah, if I just like add some extra lift on this side, I could balance that. The problem is that literally anytime you change the speed of the motor, which if you're flying a DBF plane happens a lot, that torque value changes and you can't just like easily change the wing size usually. So this is not as useful when implemented as it would initially seem.
Sometimes we have unwanted wing size change.
Yeah, rapid unplanned disassembly is to be expected, which means it's kind of more planned than not. But Sam's a very good pilot, so you can lose a lot of plane and Sam will still land it more than you would expect. Okay, I'm gonna skip the tail stuff for now because we'll talk about it later, but I will come back to it. I'm gonna try to finish off the wing stuff first, and then we can like take a break or something. Okay, so we've gone over like where you stick the wing vertically. I don't know if this is going to talk about where you stick the wing like longitudinally, because that's another control consideration pretty much. And so we talked about like planform shape. So you can also change the angles of stuff. And really the reason you would do that is that if you think about in this design, the lift that the wing creates is always directly perpendicular to the lifting surface, wherever that lifting surface is. So like right here, the lift is in like this direction. Right here, the lift is in this direction, but here the lift is in this direction. So basically, remember how we were like hanging the fuselage weight relative to the wing? If the lift is in this direction, then that means if the plane is like banked a little to the side, the like let's say it was banked just enough that this wing was completely like level, horizontal, and this wing was up a little higher, then this wing would have a little less vertical lift because it's banked more, and it would have a little more horizontal lift, and this wing would only have vertical lift. So it would have like a greater like moment basically this way than this wing would this way. And so this wing would, if you like didn't change anything else, this wing would sink back down until they were like equally banked again. Like each wing had an equal bank. Basically, it was the whole plane was level like this because of those forces changing. So you are basically hanging the fuselage in like this bowl of the wing. And that creates roll stability, which is usually a good thing. The opposite of that is means that like if you roll over, then the wing will tend to like exacerbate that roll. So there's not really that many planes that have especially that are like small like this or that are low wings that have anhedral, but there are like most of the anhedral planes that I've seen are high wings because you're already getting that effect of like hanging the fuselage under the wings, which creates some stability. And then you, since you have a high wing, you usually have so much room underneath the wing that you can like afford to have a little bit of anhedral, which decreases your ground clearance. So like the C-17 is a good example of that, I think. So it's got a little anhedral going on where the wings point down, but the wing is already mounted on top of the plane, so there's plenty of room there. And I don't know what its performance impact is exactly, because they probably did that for a reason, because whoever built that is probably a smart person, but yeah. It might be a little easier to construct. I don't know exactly. But yeah. Okay. Biplanes can also have that, blah, blah. Nobody cares about biplanes very much. Polyhedral just means you.
Oh, no.
I swear to God, these people. Okay, polyhedral just means you have dihedral or whatever that varies along the wing. So this wing has like its level, and then the polyhedral is only out at near the tips. A gull wing, such as the Corsair, pretty solid, has anhedral and dihedral, which I guess also counts as polyhedral, but because it's like this specific anhedral and then dihedral shape, it's usually called a gull wing. Well, okay, it's an inverted gull wing, whatever. That's another thing. And this thing is actually really weird because like the lift you get, like Laird said, all his equations have speed in the lift equation. So this guy was like, okay, what if I make the engines make the air over part of the wing faster? And you actually get like a noticeable like lift increase as opposed to if this wasn't curved. Because like this is basically acting as a big like section that's getting increased speed air blown over it. But you can imagine this would be really weird to build. So basically no one does this. They just tested it like once and it was cool. But okay. That's wing, like what would that be called? I don't know. Whatever view of the plane we're looking at, that's how that changes. Blending the wing into the body is useful if you want stealth, basically, or yeah, I don't remember, like Cal Poly has built flying wings before, and at least one blended wing, but I don't know why they did that exactly. Lifting body is usually bad. It's for going really fast, pretty much, because you're going fast enough that you can get all the lift you need from literally just the fuselage shape, and you don't need any wings. But flying wing and blended wing can be useful. Flying wing is one of the tailless designs because you just put elevons way out on the tips. It's kind of harder to design because a lot of the rules from conventional don't apply. But in general, you still need your center of lift to be behind your center of mass. And that determines what shapes you can do, because you need enough mass up here and enough lift back here that balances out the way you want it. Let's see. I mean, I think flying wings can be more efficient than conventional, because they still have drag from their lift, but like a normal fuselage really doesn't create any lift, but it does create a bunch of drag. So yeah, I mean, maybe that's one worth considering and seeing if it makes sense. Okay, there's a bunch of ways you can vary your wing geometry. Basically, any of the stuff we just defined, you could change in theory, and then that would change like how that thing affected your flight, like flying characteristics. But the only real reasons that you would want to change these things in the air is if you really, really needed like a certain performance at one point during the flight and a different performance at another point. So like the reason the F-111 and the F-14 have a variable sweep wing is they want to be able to go really, really fast. And doing this reduces their supersonic drag by a lot, sweeping it, but they also want to be able to land at like a somewhat reasonable speed, and going closer to a straight wing increases your low speed lift. And so they could justify that. No one can justify this, which is why it's only been done in test. There were apparently like old school planes that did this, and Mike Patey's trying to design a plane that does stuff like this. That's cool. But this is just really hard to like execute mechanically. This is not talking about folding wings on the ground. It's talking about folding them in flight. And really, they only did that on the XB70 because they realized they needed more wing area on the like a takeoff than they did it at speed because they were going so fast. But yeah, most like subsonic planes don't need a folding wing. And again, that's a whole bunch of complexity you have to design for and add weight for. The F8 had variable incidence. Incidence is the angle between, oh yeah, so the chord line is the line that connects the leading edge, like point, because the leading edge is like an edge on the wing, but from the airfoil's perspective, it's just a single point at the very front, and the trailing edge is the point at the very back. The chord line is the straight line that connects those two, and the camber is like the line that determines the profile. So all wings have a straight chord line, but the camber can vary however you want it to get the airfoil that you want. But so the angle of incidence is like if the airflow is going directly left to right here, so it's just horizontal, then the angle of incidence is the angle between the chord line and the free stream. So in what I just said, it would be the angle between the chord line and horizontal. So I don't know, like 25 degrees or 30 degrees or something, whatever that is, 20 degrees. And I don't know how much Laird talked about angle of attack, but the reason angle of incidence is cool is that you get like free angle of attack basically. So instead of having to pitch the whole plane to have some basic angle of attack when you're just flying level, you could just have the fuselage level, but the wing is built to have angle of attack already, and that's what incidence is for. So the reason the F8 had variable incidence was when it was taking off and landing, they wanted more built-in lift, and so they just added angle of attack to it. But when they're at high speed, they don't want that extra angle of attack, so they made it so it could rotate back down to very low incidence. Okay, variable camber is actually one of the most common wing shape changes because this is basically just flaps and this is basically just slats. So flaps are the name for, I mean, this is also, variable camber is also just how like ailerons and most control surfaces work. But if the, if it's only designed to do this when you need more lift, then this is called a, or like more lift for the whole plane. This is called a flap, but all control surfaces really just vary the lift that the wing is creating at that point. A slat basically does the same thing because if you look at a whole bunch of airfoils, you'll notice that basically the more intense the camber is, basically, like now the chord line actually goes outside the wing because the leading edge is now here and the trailing edge is now here. So if you connect those with a straight line, the chord line is down here, whereas the camber is still basically through the middle of all these. Like you can kind of tell where the camber line is because it's roughly halfway in between the top and bottom surface everywhere. So like here, halfway between that is here, halfway between these is here, halfway between these is here. It's not like exactly that, but it's pretty close. Sometimes it is exactly that, but generally that's roughly where the camber line is. So the camber line is way far away from the chord line now, like once you've got these things extended. And all airfoils that are like that tend to create much higher lift than ones that aren't like that, but also much higher drag. And so that's why you use slats and flaps on planes that need to be able to go fast, which means you want low camber, but they also need to be able to go slow, which means high camber. And so that's why like airliners use a lot of that stuff because they want high cruising speed, but also low landing speed.
Jake,
Yes.
so I'm guessing you only do variable incident wing if like you need the difference in lift to be like extreme that you can't get with variable camber.
Pretty much, yeah. So like most, like there's not that many examples of variable incidents that I know of. We can just quickly check. Yeah, there's the F8, which see that like orange part, when the wing is down, like not in landing mode, you can't see that. It's just tucked in behind the fuselage. But when it's like getting ready to take off or land, then it extends the whole, or it doesn't extend, but it like rotates the whole wing up and it's got more incidents. I don't know that there's any other designs really. I mean, I guess there was some that that use that, but yeah, it still has flaps. And so going off, this is an aircraft carrier based plane. All aircraft carrier based planes have flaps, but I'm guessing they were just like, we don't want to make giant flaps and we still want more lift than what we're getting already. And it also has slats, I think. Those might be like fixed slats or something, but yeah, they were like, we need more. So they went with the variable.
Would visibility also be a motivator for that kind of thing?
Maybe. I mean, yeah, like because visibility was pretty bad on old fighters anyway, and it's very important for landing on a carrier. But like, I don't think the visibility would have. I mean, I can go look at the F8 article later and see if that was a factor.
It might be that they could have more easily done that with a droop nose.
Yeah, or something like that. Because I definitely have read. Where is it? Don't know what that is. Yeah, I've definitely read this article before, and I think it said that like the visibility was improved because basically you can fly the you have two options if you change the incidence. You can either keep flying the fuselage the same direction and then the wing just creates more lift, or you can get the same amount of lift and then just droop the fuselage down. And so I think they got a little of both, like somewhere in between. So I think they got somewhat better visibility, if I remember that right. But the design, like that was just an added benefit. The reason they built it like this was to have higher takeoff and landing lift. Okay.
Isn't most, I'm sorry, isn't most variable incidents designed for the tail? Like most examples of where variable incidence is implemented is in tail design.
Yeah, I don't know that that's actually referred to as variable incidence, but when we get to tails, there's something called an all moving surface where there is no like fixed horizontal stabilizer portion. The whole thing just moves, which basically is varying the incidence. But I mean, the reason this is like listed separately is like an all moving tail moves like continuously. Basically, it's always moving. Like whatever you do with the control inputs will move the tail. This is supposed to be like a set it to one setting and leave it there thing, as opposed to like moving constantly. Like you can either set it to up or you can set it to down. So that's why I don't think tails are usually referred to as having variable incidence, but they do. You can have a tail where the whole thing can change its angle of attack, which is called a null moving tail.
Okay, thank you.
Variable thickness is, I feel like, very uncommon. Added thickness basically adds drag, but also room for structure and stuff. So usually you just design to a thickness that works for you. Although I don't even know how to do that very well yet. But yeah, very uncommon as far as I can tell. Polymorphic wings are like an old school thing for when you wanted your biplane to fold up into a more convenient shape or something, or you just wanted, you were like, oh, I'm going to take off with 2 wings. Psych, I only have 1 wing now. Not a thing we really use. And I don't think this might actually be illegal under DBF rules, because I think you're not allowed to change like some things, such as where your wings are at.
Yeah, I was just gonna ask that because I wanted to do that.
Yeah, I think you can have a swing wing, although again, there's really not much point. But I might be wrong about that. But I would definitely feel like they would frown on this idea. And you definitely can't have, like, the AIAA rules also include like all the AMA rules, the Academy of Model Aeronautics, which also includes like all the FAA rules, and you're not allowed to drop things from planes basically. So not a good
So
idea.
how about we like take off on like a paraglider and then find some way to retract it into the fuselage?
Design it and then we'll talk about it. Okay, so this was like those little things that I said I was going to talk about later. A winglet is just another way of reducing the wingtip vortex, because basically this whole area is blocking the vortex from getting through. So it's not perfect, and you just get a smaller wingtip vortex up at the top, but still smaller. So this basically increases your effective span, I believe that's what it's called. But you don't have to increase your like physical span. So that's cool. Lots of planes use winglets now. They're really like almost free lift. Like their lift benefit is definitely more than their weight in most cases. So I wouldn't rule them out by any means, even though they're usually on larger planes. It's always worth considering. And then there's lots of other stuff. Strakes are just those little weird things. They're basically like, once you start to get into like really fine control of where your airflow is going on your plane, which is not a level we usually ever reach, you would start to add strakes in a couple places and stuff, but we usually don't. And chines are basically, if you're not an SR-71, you probably don't need chines. And then if someone built a plane with a mustache, that would be hilarious. But it's like usually a retractable canard. We will talk about canards with tail stuff. And okay, yeah, so the rest of high lift devices, which we kind of briefly covered, flaps, there's a whole bunch of types. And they can either like actually change the wing area. So like, what was that? Where are the types? Okay, so here's a bunch of types. Fowler flaps, yeah. Fowler flaps will actually, that didn't help at all, make the wing area greater because they can like extend past the original position, whereas like a plain flap or split or slotted just change the camber. But like airliners use like combination flaps where they have, that's not what I want. They'll have like a whole bunch of different tiers of stuff coming off because they benefit greatly from the massive like variation in area and camber that creates. But we usually use like very low key flaps, like plain flaps or something, because we don't need as big of an impact. And it would be much heavier and harder to create. A leading edge flap is a little bit different from a slat, I think, because it basically just rotates. It's literally a flap, but on the front, whereas a slat is technically like a part of the wing that extends forward instead of just rotating. But I call pretty much anything that is a high lift device on the leading edge a slat. A cuff is just a not moving slat, basically. What else? If you have like transonic or supersonic planes, then you might want these things because your wing will be swept and you can benefit from some stuff that contains the flow that way. But we don't really use that. Vortex generators exist basically to create vortices on purpose, which does add drag, but it also will the reason vortex generators are used on cars and on like low speed aircraft is that they can get better, like they can keep flow attached longer and therefore have an overall smoother flow around the whole vehicle if it's made turbulent intentionally by VGs, as opposed to letting it go from laminar to turbulent on its own and then like have chaotic breakdown and detach. And we don't really use them, but you're welcome to look into it because we do actually fly in the regime that I think they could help. Leading edge root extensions are really only for really high angle of attack flight, so not a huge deal for us usually. And then, oh yeah, if you ever hear about interference drag, that's what this stuff is for. It's not the biggest source of drag, but it definitely is a source of drag. And these things can be really light because like on a relatively medium scale plane, this could basically just be made of like fiberglass. It's not a structural part. It's just there to reduce interference drag basically. So you can get some free drag reduction with that sometimes. And then, yeah.
Hey, Jake.
Other things, yeah.
I had a question earlier about
Sure.
blended bodies. So like
Yes.
you guys just kind of mentioned like I just forgot the name, the little thing.
Root fillets.
Yeah, roof fillets. Why don't you blend all the bodies of a plane all the time? Is it because of the weight? Like, wouldn't it help with interference drag?
Yeah, so like a blended wing body definitely has much lower interference drag. I mean, the actual wing to body itself, I would assume, has basically no interference drag or very negligible interference drag. And most planes do actually have like some kind of interference drag reduction
Right.
in most places. The places like where I've seen it in a serious design that doesn't use it is usually only because it would get in the way of something else. So like a Cessna 17, like all the Cessna aircraft, for example, they don't have these because right where the wing meets the fuselage is also where the door is to the plane and like the window. So if you had this, it would block the door. So they basically don't have the option to put one in there. But literally on like the landing gear leg that's right below that, they do have fillets because that strut would have interference drag with the, oh yeah, on the strut too. These would have interference drag with the body, which would be annoying. And so they put like a really little simple fillet in there to reduce that, even though like it's probably not that big of a difference. It still helps and it's really cheap. So they don't have one here because literally like you see that window there, that window is attached to the door. So they can't fit one in there, but like every airliner ever, their root fillets are basically built into the wing. So see this thing, the landing gear lights, this whole wing box that goes through here basically has a root fillet built into it. If I could only find a picture, yeah. So see how this isn't just like the wing just like smashes into the end of the fuselage and just has a sharp line there. The whole thing's kind of like smooth together because that will help your interference drag.
Okay.
What else? Yeah, anything that would just be sticking out. So like if there's an antenna here or something, they like to put a fairing around it because a streamlined body, which is like a fluid flow term that you'll probably learn eventually, has much less drag than most, like pretty much any other shape, including a sphere or a cylinder or whatever. So the more streamlined you can make things, which that word literally comes from, like, when you take fluids class and learn about streamlines, the straighter a streamline is, the less energy is transferred from the fluid to the object. And one way, like a plane wants to transfer as much energy as it's designed to into lift while transferring as little energy as possible into drag. So if you have stuff that's going to be generating drag and you have a way to make it generate less drag, oh wait, I was explaining streamlines. So the more you the more abruptly you deflect a streamline, the more energy gets transferred from the fluid to the object. And in case a streamline isn't, in case it's not clear what a streamline is, it's basically like the path that a fluid particle follows as it moves past the object. So like, maybe I can just look it up quickly and spend time on this. Okay, here we go. All these blue lines are streamlines, and like the ones that are barely deflecting, they're basically like they're losing very little energy. The ones that are deflecting a lot are losing more energy, but this wing is trying to deflect these streamlines because by deflecting them, well, it's not like causal exactly the way I'm explaining it, but because it's able to deflect the streamlines like this, it can generate lift. It also generates drag, but drag is a cost of lift. So, but if you want to generate the lowest possible drag, then you would want the streamlines to be as straight as possible. And a streamlined body is one that has been modified to change the direction of the streamlines as little as possible. That's why we call things streamlined. Okie dokie. I think that's all the wing stuff. All I have left is tail, which is its own whole thing, but like we're only gonna get into the basic layouts and stuff basically. And then I'm gonna do a little fuselage and multi-engine stuff. But now is a great time to pause, I think, if anyone is falling asleep / hungry / needs to go away for some reason for a minute or whatever. And also so I can drink water, because that's like twice as much talking as I did all of last week.
Thank you, Jake.
Also, you can ask questions if you've been sitting on one.
I have another one. Why didn't DBF do tapered wing last year or this year?
I feel like we very rarely do tapered wings, and honestly, I don't know why. Yeah.
I have a couple answers. I guess
Sounds
the
like
main
it's all 'cause of
reason.
Johnny.
Yeah, me. I made a rule: no taper.
It's because of Johnny, isn't it?
Yeah. I usually find a reason to blame me in a lot of stuff. I think the main reason is just it's unnecessary added complexity in the manufacturing of the plane, of the wing. When there's some.
That would be my guess too. But
yeah,
honestly,
it's just
Johnny,
easier.
if I think about it, the way we build wings, I feel like it wouldn't be that hard. Like literally, okay, so I have no idea if or when you guys would find out about this, given that like building the actual plane is like the lowest priority right now. But our like primary construction method for our like full fidelity, gonna go send it to comp planes is like laser cut the spars and stringer. Do we have stringers? I don't know. And the ribs, which are like the ribs are basically shaped like airfoil sections, and the spar runs the span, like from the root to the tip, and it would be really easy to design, at least just a bunch of ribs that have varying chords and then connect them in order with a yeah, like the geometry I feel like wouldn't be that hard. So I don't with foam, which we used in the past for sometimes, and foam is good for prototypes because you can build it a lot faster than oh yeah, and so you put all the like wood pieces together from the that were laser cut, and then you cover the whole thing in like heat shrink plastic basically, and that's like how you get your outer surface. Whereas with foam, the whole thing is like solid usually, or at least it was solid, and then sometimes you cut the middle out. But it's harder to do like compound 3D shapes. It's a lot easier to do just like a constant cross section thing, because the foam cutter, like it uses a heated wire to cut through the foam. So you have to be able to connect the 2 points, which you can do in a tapered wing. You just have to have the computer do it, I guess. And because we have a CNC foam cutter, but you basically have to trace like equal points of the of like the root section and the tip section at different rates, so that you're like so that the wire is always on the surface of the wing you're trying to cut out without ever like cutting into it. So it's harder to make out of foam, but I feel like we could probably try it out of
it says auto resigning in 10 seconds. 10.
Yeah, I think the reason we haven't done it
7.
a lot before is we didn't have a club-owned
True.
what is it, laser cutter.
Yeah.
Now that we have our own laser cutter, I feel like it would be pretty simple, but we would have to do research on our scale of planes to see if the
Damn, Peter.
you live next to a that must be annoying if you live next to a fire station.
I don't, but I live off a pretty like good street, so yeah.
So I think there's not enough research on our scale of planes where if we did do a tapered wing, we don't know what the added benefit and what the cons would be with that. Definitely something we should look into now that we do have the availability to produce it rather quickly, because we do have it in close proximity to us, the laser cutter. Do you have any additions, Laird?
Yeah. The reason in the last couple of years that I think we haven't thought about doing, or we haven't done tapered, is because of, as they were saying, like the prototyping. And then by the time we get to, like, I guess all of the benefits are kind of smaller on our scale. Like it's like weight savings, but that's not the biggest source of our weight.
Yeah. Right.
It's very small weight savings, which, like, if we were going for like the absolutely perfect design, we probably would have done that. But by the time we were getting to that level of like tweaking things, we're like kind of in a rush to get a report in and stuff like that. So it's mostly just been a convenience thing of the costs aren't that high, and the time it takes to like actually do that and design it is just we haven't considered it worth it. We manufactured a flying wing a couple years ago, which that was obviously tapered, and so like we've had the ability to do that, but
a rectangular flying wing.
Hell yeah, Boda. Was our laser cutter actually like up and running and available for us to use before lockdown?
Yeah, we used it.
Okay, because it can't have been that long before that, right? Like in fall 2020,
We had the
fall
laser cutter.
2019, was it working?
We had the
Our
laser cutter
sophomore
all,
year.
all last year. Yeah.
Okay.
Yeah, our sophomore year, it was all
Well,
up and running.
We should have built more planes then.
We should have.
But
Next
yeah,
year, man, we're gonna have like
it's almost
100
like
prototypes.
flight test is a useful thing.
Yeah. Right.
All right.
So
Yeah.
one just rules question.
Sure.
Is it required that you land in a condition where you can immediately take off?
You cannot have significant damage upon landing.
I'm not talking damage. I'm talking like controls that only go one way or something like that. Like where you
That
have to
sounds like
manually
damage.
reset. It's not damage because it's intended to do that and you can reset it. It's just that you can only reset it by hand. There isn't a...
Oh, so you can't, like, if you press a button for flaps to come down and there's not a button to bring the flaps back?
Yeah,
what you're
exactly,
talking
that
about?
kind of thing. Like you can, like your flaps are only driven one way.
Why?
I think
And also,
so.
as a pilot, that makes me very uncomfortable.
I don't think we've ever done. Well, actually, no, we have done that with the locking wing when
But
we.
that wasn't in flight.
Yeah.
Yeah, that's true. We went up to the flight
Sweet
line with
grandpa.
with folded wings. We pressed a button, and the wings unfolded, and we had to manually reset that
Yeah.
after the flight.
That was like mandated by the rules, though.
Yeah, that was
Yeah.
like that. Yeah. I guess I don't see a reason why you couldn't do that from a rules perspective. I also can't see a reason why you would want to.
I was just thinking of ways to do the whole paraglider thing.
Yeah.
Of course.
Oh, also, are we
Vlado's
allowed-
understanding or thinking is beyond our
Yeah.
understanding,
Also,
Larry.
are we required to land on landing gear, or are we allowed to land on a parachute?
No parachutes. They said that.
Yeah, no parachutes. Your lifting surface
Has to be a wing, and it
cannot
can't be a rotary wing.
Yeah, cannot like change throughout the course of the flight either. Like I guess you can have variable geometry, but like it can't be a different surface that is causing lift at different points. I
That
think.
might cause problems for the
Yeah.
whole paraglider
They
suggestion.
basically write the rules to make it so that you must use a fixed wing aircraft
Yeah.
in order to be in compliance. You can use most of the common methods of varying that fixed wing, but you can't like jettison your wing and parachute down or
Well, I just
detach
wanted
one of your
to-
wings and then
I was just thinking
Yeah.
that if I can figure out a way to do the paraglider thing, then I don't have to care about takeoff distance in flight configuration. And so I might as well go all the way and make a plane that I couldn't possibly land.
I feel like
I'm trying to think if the rules would explicitly prohibit like an actual, like, you know how a powered parachute is like close to a paraglider? Like, is a powered paraglider different from a plane in terms of the rules or not? Can't tell.
I don't
It's
know.
just a soft wing.
It's just a soft wing.
Yeah, but like, I mean, if it has, well, so I don't actually know what I mean by paraglider because I don't know what Vlado means by paraglider, but
I mean, the rule I think I would run into here is the one about still flying on the same lifting surface, because the idea is that you take off getting most of your lift from a pretty big paraglider wing, then pull that all into the fuselage and then fly on a much smaller normal rigid wing until you try to land it. Maybe succeed, maybe don't.
go ahead and read the rules and get back to us because I don't explicitly remember if they forbid like soft surface wings or not, like flexible wings basically, because I feel like they did, but honestly, I can't remember. Okay.
Yeah, I'll have a look.
I think it's time to talk about tails. So unless anyone
We didn't get a
thinks
break.
that was the break, Peter.
That was the break, Peter.
No.
Peter, you are welcome to take a break, and you can come back whenever you ready. It's being recorded. So, okay. I'm going to talk about this part on this page first, but then I'm also going to go to this page. So there'll probably be some duplication. Okay. Yeah, so as mentioned here, a regular wing is not pitch stable. It has to basically be intentionally designed as a flying wing if it's going to be pitch stable by itself, and most wings are not, so we need another horizontal surface, and usually we put it in the back. I feel like now would be a good time to mention this, but for conventional aircraft, the place that you generally want the center of mass to fall in relation to the wing is around a quarter of the chord back from the root to the from the leading edge root to the trailing edge root. Well, not the root exactly. So if we take this swept wing, I'm trying to remember what this thing's called, but you can create an imaginary wing out of it that's not swept, and it's the effective wing or something. But basically, the quarter of the way from the leading edge of that wing to the trailing edge of that wing. So it's not a quarter of the way from here to here for this wing, or from here to here, but it's if you kind of averaged this wing out into a straight wing, it'd be a quarter of the way from that wing. I mean, a quarter of the way from that leading edge to that trailing edge. That's where you want the center of mass to fall, basically, to have a controllable aircraft. And when we start to talk about tail design and controllability and stuff, that we'll go into a lot more detail about that. But that is based on having a wing near the middle and then tail at the back. So some of these configurations clearly will have nothing to do with that. But yeah, so conventional tail is just wing at the front, tail at the back. Canards are literally just mean the control surface is at the front. So that means you put the wing at the back. There are some benefits to that for certain uses, but they're not automatically better. A tandem wing kind of doesn't have a horizontal tail. It just has two wings, and one of them or both of them can, because they're not the reason you can't really use the conventional wing placed near the center of mass to control pitch is because there's no moment arm on the control on the ailerons in the longitudinal direction. So to change the pitch, you have to create a force away from the center of mass. And if the center of mass is literally inside the wing, you're not really going to be able to get any moment around the lateral axis to change your pitch. The tail is very far from the center of mass, so that's a good place to put some control surfaces and get a moment going. But in a tandem wing, neither, I don't design these, so I don't know exactly where the center of mass is, but I'm going to assume it's somewhere near the middle here, which means you can have both or either wing be controlling your pitch because they both have some kind of moment arm away from the center of mass. A three surface is just canard plus tail. I don't know if or why it's better. I mean, it definitely will give you more maneuverability, I guess, because you just have more things creating forces for you. So maybe one plane that I know kind of does this is the Su-33. which I think just does it because they can't like make their tail surface any bigger. It's already freaking huge. And presumably it would like have ground clearance issues or something. So they also add a canard, kind of like it's like a little baby canard. Outboard tail. This is the Spaceship One, I think. I don't know what the actual benefit of this is, but I'm guessing like it's probably something to do with the fact that when there's a rocket engine in here, it gets hot. So maybe that's why they do that. And then tailless. This seems very sus and feels unnatural to me. So you basically need to have control surfaces far enough back that you can make it work. Okay. Pretty much, this is almost entirely talking about the horizontal tail, because really any plane needs a vertical tail regardless, because if you have no vertical tail, the plane can just pivot around the vertical axis and there's like no yaw stability. There's very few planes that get away with not having any vertical surfaces at all. And it's because they have some other way to control their yaw. So like the B-2, for example, which if you haven't seen it recently because you didn't watch the Super Bowl, looks like this. It has no vertical surfaces, but they came up with a way to control its yaw by, there's these like spoilers basically. They let's see, B2 yaw control. There we go. So they split open like that, and if it's like so on this side, when the spoiler opens, here's a really tiny, not helpful diagram. When this that's open on both sides because it's landing, but when this splits open, it increases the drag on this side, and there's no corresponding increase on this side. So it pulls this wing to the right, and the whole nose turns to the right. Opposite thing on the other side, so they can control their yaw by just increasing drag. And they can also use that as just normal spoilers. But
do you think those are like automated, or do you think the pilots like are actively controlling those?
It's both, because the like maybe this will be useful to get into at some point. Oh, is this a Kerbal B2? But the pilot has direct controls. Controls that correspond to changing pitch, changing roll, and changing yaw. They can be varying levels of like direct authority. So in like really old school planes, and even some current planes, like if you move the thing that changes the pitch, it literally moves like a bar or a cable that's directly linked to the elevator and turns it, or the ailerons and turns them, or the rudder and turns it. But in lots of more modernized aircraft, there's a computer in between the control inputs and the control surfaces that basically takes the control inputs and looks at them and goes, okay, what do you want to do based on this? And then I'll try and move the control surfaces to do that for you. So
is that what fly-by-wire is?
Yeah. So if you have a fully computerized control system like that, then your controls are fly-by-wire. You can have some like, I think it's called like augmented control system that has some like feedback dampening or like input modification. That's not a full fly-by-wire, but this plane is full fly-by-wire, etc. So the yaw damper, which is how the computer controls the yaw, will basically always try to keep the plane coordinated, which means that the nose is pointing in the same direction as the velocity vector. And if you're uncoordinated, the nose is pointing in a different direction to the velocity vector, like you're yawed in a direction that's not the same direction you're flying. But so by default, the yaw damper, the computer will control the yaw damper to keep you coordinated. But if you give a yaw input, then the computer will factor that in, and you can intentionally change your yaw out of coordination if you want to, or like if the yaw damper is broken or not on or whatever, you can control the yaw manually. But most modern aircraft very rarely use that, like the pilot very rarely uses the rudder now, especially in jets, because in propeller driven aircraft, especially ones that only have single engines, you have to use the main thing you use to counteract that torque that I was talking about in the beginning, as the torque from the motor and the, well, there's like 4 separate things that change basically the overall torque on the aircraft trying to rotate one way or the other, but you counteract that using the rudder. But on any twin engine aircraft, the torques cancel out because they spin the engines in opposite directions. And also they have yaw dampers now. So basically you don't have to use the rudder almost ever on a modern aircraft, but it still needs to be there so that the computer can do it for you, or you just have something to balance, like to keep yourself flying straight. You just don't need to like actively change it very often. Okay, I think we finished with this. Onto the empennage page. Okay, empennage is just a fancy French word for tail or something, but it generally refers to like from here back. So everything that is a control surface or that a control surface attaches to, and what those attach to. So it's like usually not considered part of the fuselage. It's like what's attached to the back of the fuselage. But yeah, this might have been helpful earlier, but those are your control surfaces. I think that's supposed to be an A340. Okay, I guess it's useful to talk about trim, but basically an aircraft that's in trim does not need any active control inputs to continue flying like in the same manner. So let's say you're flying straight and level, and then you increase your speed to just like from one arbitrary value to a new arbitrary value. So you're not speeding up anymore, but you've just sped up. You will now be out of trim because the lift generated by your wing has changed because your speed changed. The lift generated by your tail has changed because your speed changed. And until you retrim the elevator, the plane will now start to, like let's say you sped up, the plane will probably now start to pitch up because the moment on the wing increased more than the moment on the tail. And so you now have a net like upward pitch moment. So to make it so that the pilots don't constantly have to be like holding in control inputs all the time, which gets very tiring, trust me.
They have like a PID system?
In computers, yes, but the original system was literally just like a wheel or a thing you could move basically, and it would move a trim tab, which I don't know if there's a trim tab shown on here, but there's probably one shown on here. Those are just the cables. Oh, here we go, trim tab. Okay, this wheel, if you turn it, changes the trim. I just want to see the actual trim tab. What? Okay. It's basically just a tiny control surface on or next to the existing control surface. So you got the elevator, and then you got the elevator trim, and you got the rudder, and you got the rudder trim. So, and then you can also have it on the ailerons. That's very small, sorry. But basically, it'll deflect in the opposite direction of what the control surface normally does. So that, like, let's say if I deflect the pitch trim tab down, then that's going to push the whole elevator up, which is going to push my nose up like that. Because if the elevator goes up, the airflow pushes it down, so the tail goes down, so the nose goes up. So if I am pitching down continuously, then I want the pitch trim tab to go down. and I don't like have to think about this a lot because you just spin the wheel and you know which way to spin it, but or at least they designed it to spin in a way that makes sense. But I can change the position of the pitch trim tab to change the neutral position of the elevator so that I don't have to constantly give a control input to hold the nose in the same place. And so if a plane is flying in trim, that means all of its trim like controls are such that it's like not changing flight state. It can still be accelerating because you can be in trim in a turn and you're accelerating if you're turning, even if your speed is constant. But it just means like if I wanted to be in a steady turn and stay in that turn, I could trim for that turn and then I would be in trim. And flying in trim is good because it's like the lowest drag state for any flight condition. And it's also easier on pilots. So yeah, our like aircraft, they don't have trim tabs, or at least I haven't seen one built with trim tabs, but they do still have trim control because, oh yeah, it basically works like this, I think. Actually, I don't know. No, there's a different thing. But our aircraft, the electronics that control the positions of all the control surfaces, it's commanded, like the transmitter that the pilot's holding sends signals to the receiver that's on the plane, and the receiver sends the signals to all the servos that control the position, and there's controls on the transmitter to just mix trim into the control signal. So if all the controls are neutral, but you start changing the trim, then it just says change the control surface position by like an amount relative to this trim amount. So that way you don't have to hold the control input, but you can still get a new constant control position. Hopefully that makes sense because it was not very simple to explain. Hopefully that okay. Yeah, I mean, you don't have to worry about it that much unless you want to fly a plane. Okay. Okay, I guess we can get on to actual tail configs now, which would be great. Okay, so for the tail plane is like the relative position of the well, okay, so we're defining the tail plane as just the combination of the horizontal stabilizer, which is a part that doesn't move, and the elevator, which is a part that does move. And all of these things can pretty much be like they have analogous properties to the wing. So you can change the planform and the airfoil and whatever else and the position. But because the tailplane is pretty small, you can mount it on like in different places, and you can also either mount it to the fin, which is the vertical version of a tailplane, or you can mount the fin or fins to the tailplane. So fuselage mounted is kind of the most conventional or straightforward because you just attach the horizontal surfaces to the fuselage or like to each other, and then that to the fuselage, and then the fin is also there. You could attach the tailplane directly either somewhere along the fin or at the end. If it's at the end, it's called a T-tail. The benefit of doing this is, see how the wing and the tail are kind of like in the same plane? That means the wing lift process is probably going to mess with the tail process a little. And so if you make a T-plane, this is now doing its own thing and this is doing its own thing, so the tail can be more effective like this. The downside is that when you have high angle attack, such as when you're stalling, the whole thing, I'm gonna have to image search this. Okay, the tail basically can get trapped in the detached flow behind the wing, and it becomes like useless, which is bad. It's another picture. So like in normal flight, it's good and fine. They get their own stuff, but it's bad for stalls. So that's just another thing to consider. And then like Laird was talking about, you could also have it be so that there's no like horizontal stabilizer technically, because that is defined as the part that's not moving. So if the whole thing is moving, it's just an all moving or flying tailplane. And you can have that for either surface. Okay, ways to mount the fin. You can have two if you need more stability and you don't want to make the one of them huge. You can mount them on the outsides of the tailplane or on their own booms and then connect them, or just on their own booms and not have a tailplane for some reason. You could have three of them. You could also have them be on the bottom, which makes a lot of issues with ground clearance on takeoff and landing, but I actually still don't know why you would do this. So I know why you would do it on the X-15, which is on like re-entry, basically. The vertical was, like the top vertical is basically completely masked by the body at high AOA. So maybe it's only good for high AOA applications, but then like the Reaper also has it, and I don't know why. Or not the Reaper, the Predator. I don't know, one of those has a ventral V-tail, but it's a weird aircraft anyway. So yeah, and then booms and stuff. I'll talk about that a tiny bit at the end. A V-tail just mixes the vertical and horizontal tail. I mean, yeah, that's right. So it's not like that much better or anything. It does look cool. And we've built one once when we needed the whole tail to like fold up against the body, because it's smaller a little, like if you need to fold all those things away. But other than that, it's not that commonly used. Yeah, basically use an X-tail if you need your plane to take off sitting on the tail. Otherwise, it's probably not necessary. Outboard tail, again, is like on Spaceship One. Honestly, I still only think like this is a whole freaking rocket motor right there, so you probably just don't want to attach the tail to that. Otherwise, I don't know why exactly they would do it like that. And tailless is basically for flying wings, or deltas, because you have so much wing back there anyway that you don't need a whole separate tail to get enough control authority. You can just use the parts of the wing that are farther back. Okay, that's tail stuff. And then because I just want to be done and we're over time, I think technically, I'm going to blast through fuselage. So you can basically either have long skinny tube fuselage, which is like the normal kind. You could do blended wing body where the fuselage is like mixed into the wing. Oh my God, I need to stop clicking on that. You could have like a twin boom kind of setup, which I don't know if there's any of those on here, but instead of having like one big fuselage, you could have like two small fuselages, which is different from like a twin tail boom because that doesn't necessitate a twin fuselage boom, but like a P-30, or well, I guess
doesn't the Vampire have it, right? Or
the Vampire has a twin tail boom, but it still has a single like fuselage cockpit section thing. The P-38 is also like that. The Vampire is basically just a jet P-38, but I want the twin Mustang. That's like a true, yeah, that's like a true twin fuselage plane. Yeah, so, and then you can also have engines on multiple booms, even like regardless of the number of fuselages. Oh, I know a true, what's it called? This guy. That's a twin fuselage. So basically, good reason to have a twin fuselage is either you are rebuilding old planes that you think will work better like this, or you need to hang a giant rocket in between your two fuselages. Other than that, single fuselage is usually the go-to, even if you have like twin motors. Like you don't need a whole twin engine. You don't need a whole fuselage for each motor. So the only time that it might make sense to do like a twin fuselage for a twin engine is if you also then did a twin tail boom and just use like one fuselage for each engine, storage, like whatever other fuselage stuff, and tail all at once. And there's one more thing I thought other than fuselage. I don't know. Maybe that's it though. But yeah, I can't remember. Yeah, and how you lay out the tail, because I guess I didn't really talk about the performance that much, is mostly comes down to like controllability and what will work for your structure with how much control surface you need. So like if you need a ton of authority, all moving will get you a lot of moving control surface. If you need like a bunch of extra structure for your tail, maybe use multiple booms. Yeah. You can definitely read online about this probably and see what the benefits of each one are. But basically the cons to any of them that are other than the most common conventional one is that you have to do more research. You have to figure out more problems that people don't run into. It's more effort in general to implement something that is not well documented than something that is. So that is why most planes look the same, because it works, and now at this point because everyone does that. So yeah, that's a very weird looking plane. Okay, I think I'm done talking at people for today. If anyone wants to have a long drawn out conversation, now would be a good time, I guess, because I'm not going back to sleep anymore. So yeah, if not, if you're just gonna head out, then thanks for coming, and hopefully you are at least slightly more informed than when you showed up, because otherwise I did a terrible job, but we can hope not.
That was very, very informative.
Okay, well, I am good at reading Wikipedia, so.
Yeah.
All right, I'm gonna head out, but thank you for the interesting lecture, Jake. Very, cool. I actually enjoyed that. I'm not being sarcastic. It was actually really
cool.
I
also enjoyed that. Otherwise, I would not have volunteered. Well, I don't think I volunteered, but I went along with being volunteered for explaining it, because plane design is one of the most radicals in all of aerospace. So.
All right, see ya.
See ya.
Bye, Jack.
All right, thank you. See ya.
Bye bye. Thank you, Jake.
All right, so Peter and Vlado, now it's time to learn the code, right?
Yep.
We're gonna have another 2-hour lecture on how to use the.
Only 2 hours. I thought this one was gonna be 8 hours.
Oh well, I might have to abridge it because
8-hour hackathon for DBF code. He was like, counteroffer. I could just die right now. That would work.
Yeah, we'll see. Being awake is a lot of effort.
Yeah.
Okay.
Is in fact a better state.
But for what it's worth, I do have a way that I think would work to retract a paraglider.
Okay.
All right.
I don't think anyone wants to hear it, but
yeah, I was also thinking, like, if it's on a tether, will they allow you to like have your wing be variable distance from the rest of your plane by being on a retractable tether?
I don't
That
know.
feels like it'd be a hard no, but I also feel like I've never seen them specifically
because
say
I don't
you
think
can't do
anyone's
that.
ever tried. I don't think anyone's ever gotten
Alright.
shut
Well, of
down.
course, no one's tried.
I
I'm a
recommend
special kind of
Next
crazy.
year, Vlados submits his own plane to DBF, and it's just what he's saying right now. Regardless of the challenge is like build a quadcopter. He's like, no, I'm building a retractable paraglider. Yeah,
Okay.
that sounds like an excellent.
For what it's worth, I was planning on just using a kite as the paraglider
Well,
because
yes.
I can buy those.
Yeah. You're telling me you don't have access to commercial paragliding equipment? Also,
Well, 'cause I need a
just build
small
it full
one.
scale so that no one can doubt the validity of your results.
I'm not sure I would want to be on an aircraft that used any of this.
Doing
You know, that's how you know his
perfectly
design's really good.
Yes. The perfect
Like,
design, the one you would never fly in yourself.
All of my ideas here are noting that, one, even if we do build it, I'm not going to have to get in it. And two,
But yeah,
Wait,
Larry,
we didn't tell you?
do you need to record this?
Probably not.